Hello everyone, thanks for watching this video. I'm Jiawen Zhang from East China Normal University. Today, I'm going to talk about our work. The title of the paper is ORCAnet, Differentiable Multi-Parameter Learning for Cloud Simulation. We will present the following 5 points: background, ORCA motion model, proposed method, results and analysis, and the conclusion. For practical cloud simulation, it's crucial to accurately model cloud motion or understand cloud behaviors in the context. However, accomplishing this task is not easy because of many uncertainties and complex decision-making mechanisms such as unobservable agent intention, widely varied interactions across individuals. So the design of simulation model algorithms and the estimation of their parameter sets are challenges faced by the cloud simulation research. There are many works proposed to model cloud motion or understand cloud behaviors, which mainly are divided into two categories: agent-based motion model (AMM) and data-driven behavior model (DBM). AMM include techniques based on rule-based methods, force-based methods, velocity-based methods, which commonly have clear rules for cloud motion. These methods are flexible, applied to different scenarios successfully, but they often require some prior information and great effort to fine-tune parameters for realistic simulation. On the other hand, DBMS extract the current trajectory of each agent and inform the subsequent trajectory accordingly. These methods efficiently generate intuitive motion descriptions of agents without modeling complex parameters, but they highly depend on input data with limited realistic results. In real application, cloud simulation is frequently carried out with messy and easily accessible data. In this case, realistic and efficient cloud simulation cannot use the above methods directly. In our work, we proposed a novel strategy which evaluates multiple parameters using DBM and then simulate the agent motion using AMM. This strategy takes full advantages of the two kinds of methods mentioned above. ORCA is the most widely used velocity-based collision avoidance model in computer graphics, and our method uses ORCA as the basic model. The table in the left shows the definition of parameters and variables of each agent in ORCA. The core idea of ORCA is to transform the cloud collision avoidance problem into solving the optimal velocity in the half-plane as shown in Figure A and B. Specifically, we explain the role of the 5 important parameters in ORCA: ND, NN, THR, and MS. First, two parameters ND and NN are adopted to select necessary neighbor agents for subsequent computation. Second, corresponding half-plane for each agent is directly constructed with their state, TH and R. Third, the permitted velocity set is formed by the intersection of half-planes according to MS. Finally, collision-free velocity v-nu is calculated using near programming. In this way, an agent's position in next time step is updated by the new velocity computed, and ORCA repeats the process until all agents arrive at their destination. This interactive process is shown in the figure in lower right corner. This figure shows the forward simulation process of ORCA. We can easily compute gradients with respect to 3 parameters R, TH, MS via backpropagation due to its naturally differentiable calculation. However, the operation of filtering neighbors impedes ORCA model from being differentiable due to the discrete sampling calculation. Our solution is inspired by soft rasterizer, which replaced the discrete operation by a continuous approximation function for differentiable rendering. Motivated by this work, we devote to convert the original discrete operation in ORCA into a fully differentiable operation during forward simulation. Then all of parameters in ORCA can be optimized automatically via backpropagation. In our design, two parameters nd and nn are linked directly to the subsequent differentiable function, and the non-differentiable neighbor searching is replaced by a continuous approximation function. Specifically, we use differentiable Gaussian corner to approximate the responsibilities among agents in ORCA. The new formula of velocity is displayed above the figure. The left figure shows the difference between ORCAnet and ORCA, and this formula implies that the error between ORCAnet and ORCA will be smaller with smaller d. Farther from the original half-plane leads to weaker constraint in choosing the new velocity. This is consistent with the real-world observation and the common sense that people care more about the collision avoidance with closer pedestrians, and the further pedestrians may be ignored. We can control the relative error of ORCAnet compared with ORCA by adjusting sigma. The right figure shows the difference between the original and the approximate formulations. When sigma gets closer to 0, the error will be more serious. Therefore, we set larger sigma to guarantee the preciseness of ORCAnet in our experiments. For the parameter estimation, we connect multiple ORCA in the networks. The whole procedure is fixed at t time steps. Black arrow represents the forward computation to generate predicted position and velocities. The parameters are updated at each optimization epoch by the backpropagation according to the loss function, which is represented as yellow parts, and we can change the result by changing the weight factor. We first generate two synthetic datasets with different number of agents for the subsequent experiments. Then we evaluate the simulation accuracy of ORCAnet with an open-source ORCA framework to demonstrate its effectiveness to approximate ORCA. We can see that the error decreases as the hyperparameter sigma increases. ORCAnet reproduces the same forward simulation as ORCA when sigma reaches a larger value. To quantitatively elevate the accuracy of parameter estimation, we first use the synthetic dataset with 10 agents. In this experiment, we know all the states and the parameter settings to validate the performance of ORCAnet. From figure A and B, we can see our model can effectively reduce the loss by updating the estimated parameters via backpropagation. Figure C and F shows that MS and R decrease most intensely in the early stage and quickly converge to the ground truth. Figure D shows that ND updates most slowly than other parameters. However, this is caused by the choice of sigma. The gradient with respect to ND will become smaller because sigma will be the denominator in our formula after derivation. Though smaller sigma can accelerate the update rate of ND, it may produce different motion compared with ORCA. Besides, ND can slowly update until convergence with different sigma. After about 2,400 steps, the update rate of ND suddenly becomes smoother. Fundamentally, when ND gets smaller, it will reach a threshold value to narrow the neighbor searching range. ORCAnet learns to optimize parameters through interactions with other agents, so when NN decreases, it may lead to fewer constraints and more uncertainty. So we can see the violent oscillations of MS and R around the ground truth after about 2,400 steps. Figure E shows th does not get updated in this process, since we coincidentally set th to be in a reasonable range in the random setting, and under the specific scenario, the change of th will not produce a various effects during the forward simulation. Then we do the same experiment in the synthetic dataset with 50 people. Compared with the previous experiment, the loss decreases faster and all the parameters converge more quickly, because as a collision avoidance model, ORCA performs best for medium density clouds, and ORCAnet can have a better performance in this case. All parameters convergence rapidly except ND, as shown in Figure D. Because for a particular scenario with a finite step size, ORCA allows multiple possible parameter combinations to satisfy the same trajectory, and the ORCAnet will learn the parameters that are closer to the real value with longer sequence. In this case, ND converges towards a closer value compared to the ground truth, and the learned parameter setting can also produce similar forward simulation results. We test our method in two real-world datasets, considering that the initial value of the estimated parameter has a great influence on the convergence rate. We are supposed to select the proper initial values for each individual. As shown in the table, we employ the parameter configuration proposed in reference 27, which can represent various types of cloud movements from cloud trajectories in ORCA. In this experiment, we select the initialization parameters from the table for each agent and adopt the best optimized value as the final result, and the results show that our parameter estimator also works robust and efficiently on real-world dataset. And we also conduct an extrapolation experiment to further verify the effectiveness of our method. It shows our method can drive the future motion in a short time accurately based on the optimized parameters. We also compare with another parameter estimation method, genetic greedy, which is the combination of greedy method and genetic algorithm. It can be seen that the trajectory optimized by ORCAnet is closer to the real path in the first half, but in the second half of the trajectory, both of optimized trajectories are far from the real-world dataset due to limited capabilities of ORCA. In spite of this, ORCAnet performs better than genetic greedy. In our work, a novel and differentiable ORCA model called ORCAnet is presented. The classic ORCA model is placed in the deep learning framework, and Gaussian corner is used to approximate the rule of neighbor distance in collision avoidance, which turns the original discrete operation into a fully differentiable forward simulation and ensures the reliability of the simulation. And we leverage ORCAnet to optimize the parameter combination from synthetic and real-world data by taking advantages of the automatic backpropagation performance of modern deep learning framework. Our method can rapidly converge to correct parameter values, and we generate the input synthetic sequence. The realism of cloud simulation has been significantly improved through ORCAnet. Various experiments on synthetic and real-world datasets have verified the effectiveness and robustness of our proposed method. Thank you for watching.